So we'll talk in English. My name is Lev Faivishevsky. I'm a departmental data science expert from Intel Advanced Analytics Group. And today we talk about using deep learning to detect video distortions. This is a joint work with my colleagues, Ronella Perdon, Benjamin Melul, Ravid Ziv, and our chief data scientist, Amitai Armon. So I will talk a few words about our department. This is actually a large group of 150 data scientists, big data developers and product experts, and also students. We located in Israel. We have a few campuses, and Petah Tikva, Haifa, Kiryat Gat, Jerusalem. And actually, we do a lot of things which may be separated into categories. One of them is transferring Intel operations, and the other is building smart products. Regarding to the things that we help Intel, are those things in design. So we make our validations of our silicon better with machine learning. We also help to manufacturing to lower the cost and to build even better chips. With regard to the sales and marketing, we use our analytics to scale it and to make a big ROI with a lot of work on text. We also build some products. We put in AI in our embedded systems. We use industrial AI, or what was once called IoT, to detect malfunctions in machines in different occasions. And also we do health analytics, which is very fascinating thing we do. We enable smart clinical trials, and we cope with several diseases. So this is also very interesting. We create an annual value of several hundreds of millions for Intel, and we intend to make even more in each year. So today we'll talk about one of our projects. This is using deep learning to detect video distortions. So we see here that there's frame and here's distorted counterpart, and we would like to make a detection of that. So what is actually the use case? Use case here is that the Intel processors, as you surely know, have a built-in graphics unit. And the validation of this unit of these drivers includes checking that actually movies are played well and the games also looks good. And this detection occurs without reference. So we have only the actual image that we are looking for. And this is was done actually by people that looked on every screen and tried to detect visual corruptions. So this is actually examples of some corruptions. You see that the corruptions may be very small and easy, not easy to detect from the first sight, on actually looking even with more attention to a picture. So this is a tricky task. So then they looked on this project. We have a few goals here. So this includes actually to make the detection faster, actually improve the quality and reduce cost of making such validations of graphics units. And actually the approach that we adopted, that they refocus our actual workforce of people that look only to go through the system alerts, not go through the whole films, but actually focus only on the suspicious moments, and actually by this greatly reduce the workload on the operators, and thus enabling them to make more. And to do that, they actually mimicked the old work of the human operator, actually by capturing the screen by a camera, so to model the whole process. So they have the end-to-end system that starts from playing some content on the video, looking on the screen with the camera, and then automatically analyzing this video stream by our modeling system. So actually, this is an ambitious goal, and this means that it comes with a bunch of challenges. So The first challenge, actually, that the thought of, and it's actually a good challenge, is that here we need to identify noises in a picture and not the objects. So actually, if you think about the modern machine learning, and it's maybe a main general task like looking at ImageNet or MNIST, we have, in this case, it's a few predefined categories of objects that occupy a significant portion of image, and would like to distinguish between those main objects in the image. For example, between cats and cars. But here, the problem is more tricky. We need to neglect the main object in the picture. We need to disregard whether it's a car or a cat and to focus on some really small distortions in the image and to detect those distortions and to neglect all other stuff. So we have over 10 corruption types which we are actually dealing with for now, and each of these corruption types have several possible appearances, so the task is tough, and this is not the only challenge. Surely, that thing that makes the detection process tricky is that we have no reference image. So in this, we need to assume that there is no reference image because we want to account for movie ads of arbitrary game actions which may spoil some golden reference that may be captured in advance, and we have some checks in the path that also have reference, but for us, task is to work without no reference. So we need to look at the video and to say whether in this specific video there is a corruption or not, there is some distortion or not, and we don't have some golden started. So more than that, the content that we work on is not very homogeneous. So we have all possible kind of content to be supported because the users or the computers do a lot of things on them, not only videos, not only games, but the combination of those very realistic, and they should be able to make a video detection system for the small corruptions that will work in this arbitrary content in various circumstances. And to make the things even more difficult, surely some of corruptions not seen in the single frame. So for example, if we have some flickering, then each individual frame may be okay, but the sequence of frames may be not okay. So we, in a sense, need to refer to the whole sequence of images or a window of a certain length and detect whether there is a corruption in this window. So we may not limit ourselves to purely per frame detection in these cases. So, but okay, if this is not very convincing, now let's add one more set of challenges. So actually we have a lot of data, and the frame rate is high, and each second we have dozens of frames which are generated, and they would like to have our system, which is automatic, to work the whole day, 7 days a week, without even stops on Shabbat. So actually it generates 2 million frames, and we have dozens of systems to be supported. So we need to see, and we need to ensure that the false alarm rate is very low. So this is the critical measurement for this project. We cannot afford to ourselves to have some false alarm rate which is high. We need to see that it's controlled and it's low, very low. And okay, so actually we are not having the manual operators to go on the whole content. We have the system, but the system, which includes camera, also have some artifacts. Maybe have some reflection or ghost effects which are occurred due to the camera issues, and we need to disregard them. We need to say, okay, so we see some lightning distortion in the image, but it's okay. We shouldn't alert on that. And to make the things the best as possible, we don't have actually a huge collection of real corruptions that were detected in the history by manual operators. So we have only few sample images of corruptions, okay? So we need to tackle all those questions, and surely the first challenge that we need label data. So if you want to make a very good performance system, the label data is essential, it's crucial. So we need to think how we do that. We cannot plant the corruptions in the image artificially, it will not be good enough. So actually, we need to reproduce driver bugs. So actually we defined a set of corruptions that we would like to detect, and we reproduced these driver bugs seen in the past, and we created these in this way the corrupted data. Okay, so we created our actually class of interest by ourselves by reproducing the known problems using the test configurations. And to make the training process be stable, in order to couple with these main obstacle of that I talked about in the previous slide, like that we need to detect the noise but not the object, our way to approach that is to include the exact reference smoothie in the training. So in the training, since we simulate the corruption by recovering a real bug, we may also have a reference video or reference video appearance for this content. So in the training, we do have both corruption and reference simultaneously. And actually, we also have a large number of unlabeled data. And we pro some system tricks using black boxes and so on and so forth to reduce reflections. So with all these tricks, what we have is not too much. We have only 5 minutes of labeled corrupted video for each type of corruption. And we have some diversity in content. And we also have the exact reference videos for those 5 minutes per corruption. And surely we have a larger amount of unlabeled good data. So this is a few examples what we have. Okay, so how we approach this problem. And actually, okay, it's another challenge. So we'll cover that as well. Actually, from the beginning, it was clear for us that the deep learning is the true solution to describe problems. And we tried to work with the several topologies and started from some deep CNN topologies, and we used both the tuning modeling, tuning the existing models and training from scratch. That proves to be better. We also use some shallow CNN topologies on full images and also dividing images into small patches. We use the CNN with wiki supervision, considering several labels together just to say this is corrupted or not without detecting the specific type of corruption. And we also looked on time-based stuff, which I will cover in details in the next slide, which included the time-based 3D CNN and the LSTM on the features. Also, we tried to employ the unsupervised learning, and the goal of this learning is to cope with the corruptions which were not presented in training data due to some limitations, or maybe during this may be useful to detect the new content and the new corruptions for the new chips to be tested. So we used the variational auto counters and also employed anomaly detection on image features. We used also surely a number of different data augmentations, sampling and resizing. So currently we use both deep CNN and we train it from scratch. It works better for us, so the task, our task is different significantly from ImageNet, so training from scratch proves to be very valued. Time-based CNN, we also have a nice model, very light and working fast and detecting good some corruptions, which is the LSTM on image features, and also have some anomaly detection of image features. To the bottom line, we have pretty good recall. We detect 80% of images or sequences of images, which we look into account. 80% of them we are able to detect the presence of corruptions. So actually, this is a very good number because think about some corruption in the GPU, in the graphics unit. It surely manifests itself in more than one frame, in more than one sequence. So if we detect 80% of each frame or each sequence, short sequence, then actually we're able to cover pretty well the possible corruptions, and we're able to achieve very low false alert rates. So we have in mind some capacity of our remaining manual operators, and we adjusted for them. So actually, thinking about that, we diminish the workload over them 1,000 times. Okay, so having actually one per mile of false alerts. So I will go through some nice stuff that we discovered in our work. So as we see, there are some corruptions, some distortions, which comes in the sequences. So here I have a small example of that, and we see that the image, the video flickers. So the same frame changes very little, but the brightness drops. This represents an important thing that needs to be caught by detection system with a good accuracy. So if we employ image detection on each frame, it will not discover anything. And because actually the only thing that may be different here is the slightly less bright frame in the middle, but we can't rely on that. So we need to address the combination and to the frames. And actually, what we do, we transform each frame into a sequence of features which we extract specifically for this corruption. And then LSTM works on the sequences of these features and is able to produce a score that represents the time evolution of the vector characteristics, and say is there this time evolution is suspicious or not. So as we use not the whole stuff of a bunch of pixels, but only certain features, that works very, very fast. Also, we looked for the specific cases which special treatment is needed for some difficult corruptions. We also have time-based 3D CNN that actually is performed by combining several frames together to make some bigger frame with possible high number of channels, high number of colors, and applying a deep CNN topology to this enlarged frame. And this actually is heavy computationally, but not that much because the use is only for the windows, and then the windows are not overlapping. Then actually we remain the same complexity as looking for result for the same network on the single frame. And it also works pretty good for specific difficult corruptions. This is a challenge to actually to deploy these models. So from our data science point of view, well, it's nice models and they give good results, so the work is done. But surely this is more than that, and we need to support 24 hours a day and the whole time running the analysis by these deploying models, and we have several of them. And actually we need to accumulate the sequences of images, which is also a challenge for a real-time system, which need to stop and wait until the specific number of frames is combined together in sequence, analyze the sequence, and then proceed to another sequence. So we built a special video analytics system to code this system. This is more general than performing only this task. And actually, we presented in the latest Strata. This is the reference to the link by our colleague Rana Vidan. And actually, it combines a lot of big data technologies working in real time. And you're welcome to go through this presentation. So actually, for the time being, we have good results. We have good confidence in that what we are doing actually provides a needed value to our internal customers. So we have side-by-side runs in progress, and we have dozens of real cases in which there were corruptions. And we're also very proud of being able to detect a case which was missed by human operators, but caught by our systems. Actually, it was done by the fact that human operators cannot wait too long, but our system works automatically all day, and actually may be efficient in the cases and human operators are also just too tired to detect some things, but we are able to detect. So that's pretty good. We deployed it in 2 sites, and we fully deployed this year. And we submitted a patent on it, and we may publish it on several workshops and conference later on. So I think it is a good time for good questions, and you're welcome. Okay. Okay, so the question is to describe the use case, how it helps to detect possible malfunctioning in the graphics units. Okay, so actually this system is able to analyze the video stream and to detect a visual distortion of that. So what actually we are doing, we take a graphics unit, a computer with this graphics unit we need to be tested, and we place it inside the system. And they use this specific computer with the graphics unit to play content. Yeah, precisely. So the task here is to validate the quality of GPU, and our main assumption here is that if the GPU produces valid visual content, both in fields and games and all the stuff, then the GPU is valid. So it sounds reasonable. And surely, if by negation, if it doesn't produce some valid content in certain occasions, that the GPU is not valid. And they detected these occurrences with our system, and later on they may be traced. Okay. Can you describe the finite model that you use? Yeah, so actually I have a slide on here, but okay, so here we see the number of models that they actually apply. So we use some deep CNN in image level. We use time-based CNN for some tricky sequences, and they also use some elegant LSTM on the features of images that runs all the time on the sequences to detect a set of corruptions, and also employ anomaly detection of image features. So this is the ensemble of models which we use, and alert of any of this model is then raised to the human operators to be analyzed. Yeah, so actually, this is a good question. We started to work from the single model that detects several corruptions in hand, but we saw that there are specific corruptions that request some specific treatment. For example, if we have flicker, then we have a sequence which may be problematic, but when it's on the frame, each specific frame is okay. So surely it's another model for this case. Okay. Yeah, we tried to understand what is the probability to see this specific content. So we need to reproduce recompose this model and to see how likely to see to obtain this combination of images. So it gives us an opportunity to make a likelihood of appearances for each image. And our assumption here is that with good training of variational autoencoder, we will arrive into a case that all possible content is possible, but content with corruption is very unlikely. It's very probable. So this is the main assumption of this task. Surely it's a tricky task because applying unsupervised model requires you to have true distributions of the data in hand. So in a sense, we need to employ to assume that we have a good representation of all possible content that we have. Whereas the supervised modeling that they use, which is looks both on the corruption and the reference data, looks only in the direction of possible corruption. So somehow it works better even in the precisely new content, which were not presented well in training stuff, in training set. So see that this is a difficult system with quite a number of challenges, and we employ different models to address each challenge. And actually we combine them in ensemble and control the false alert rate of the whole system so that it produces a good insights for our operators. Thank you.